Hello Quantum, hello Quantum. This is a game. This is a game from IBM, and I have sort of mixed feelings about this game. So the I played it a little bit, but I really didn't understand absolutely everything the way this is displayed, and how is it supposed to help you understand better quantum concepts. I thought the idea of a game might be interesting to build quantum intuition. Um, so I don't know. Let's see. I didn't go through the how to play guide, so we can take a look at this first and see if we get anything out of this before we start. Is it just your typical puzzle game? But so we have states: white is off, black, white is on, black is off, and random is the outline. So I guess that would be the equivalent of 1, 0, and then the random, it's probably whatever superposition. So then you have the controls of the game are gates. So the X, Z, H, and the CZ gate. Why just these ones? Yeah, maybe just for the purpose of the game. Let's see. See, this is what I don't really get, the way this is outlined. So, okay, the target of the game is to match the board to the target. Fine. That's just the simple game goal. And that's all what they explain you, but there's this little learn more here, which takes it to a suddenly what is quantum computing guy. Very basics, 0 and 1s, measuring qubits. So getting the right information from a qubit depends on measuring it in the right way. Despite many different possible ways of measuring qubits, two types have become our favorites. Okay, so those two slots indicate the two different measurements, and my intuition tells me that the one at the bottom is the traditional Z measurement, and then the other one is after applying a Hadamard. So yeah. Yeah. Next, IBM Q. Doesn't seem to be needed. So that's the measure. That's the measurement gate, and here you have. Okay, so what does this mean? Is okay. So black is 0. This means 100% possibility, 100% chance of just getting 0. White is 1, and in this case, okay. So in this case, and the last one you can see here in the right side, because there's an outline, it means it's in a superposition. Okay, so but this is defined as the 50-50 superposition. So after applying Hadamard gate, basically. Okay. Okay, but then what this is telling us is that the hidden, the real or the previous value or the real state of that qubit is an actual 0. Okay, it's just weird. It's weird to think of this as a way to learn quantum computing or to gain some intuition, because it's hard to understand these things enough if you haven't really gone through certain details, and now suddenly, it just, yeah, I mean, it's a game, right? Yeah, so the Hadamard and the measurement, okay. When the top circle is certain, yeah, those are just nuances, okay. Oh, now that's, okay, so that's where it's getting interesting here. Qubits all start off their life in the same way, so 0. So two qubits at the beginning of their lives will look like this. So what is the thing in the middle? So what are these 4 squares in the middle? The 4 slots. Because I understand that the light colored slots are the qubits. So on the bottom left and bottom right. When you look at the 0, you're probably wondering about the signs. Okay, this is just the Dirac notation. They're basically labels, blah blah blah. Quantum gates. So you see, just like that's it, and they don't like why there is a black circle here in the middle. Um, quantum gates, the x turns that into that, so a 0 into a 1. And then a 0. So you see, and that's where, why would the x turn both? It's like, I get it. I mean, if I don't care about that, I just play the game and that's it. But there has to there has to be some logic behind the way this has been chosen in terms of the design, right? In the image above, the x gate is placed on the bottom line since this corresponds to the qubit on the left. To do an x on to the other qubit, then we do it like that. Okay, and then the same thing happens. And now things get even weirder with the z. So we've got two qubits that they are not in the initial state here. Here, as you can see in the middle of the screen. So they are both in a superposition. But then when you suddenly apply a z gate, then you're also flipping that other stuff at the top. These operations, x and z, are examples of Clifford operations. This fancy name just tells us that they are operations with a relatively straightforward effect on circles. In fact, the visualization comes precisely from the way we like to think about Clifford operations and their effects. So and then what, the Hadamard gate, and then that flips the entire row. You see, it's tough to grasp because you try to abstract away some things to make that easier to understand in terms of what are the rules of the game, but yes, I get it. I mean, if you just want to play with by the rules, then you have the rules. But what does this relate to quantum computing? So my intuition tells me that this 4 squares might have to do with the fact that this is a two qubit system. So this is sort of information. This is sort of state information, because what is already obvious is that a 2 qubit system is not the same as two separate 1 qubit systems put together, because you have that all quantumness there, like the entanglement and all this kind of stuff. That this means there is information that's part of the system, but it's not necessarily part of each of the qubits. So my intuition tells me that's that, but I don't really get why. So it's not really obvious to me what does it mean that it's a black thing or a white thing, a white circle. Okay, let's see next. Maybe there's something else here. Making qubits talk to each other. As we've seen, limited amount of certainty in the measurement results. When programming quantum computers, our goal is to manage the certainty as best as we can. We must guide it on a journey from input to output. So far, I mean, I like the way this is phrased, and I think that's an interesting way to phrase intuitively what quantum computing is about, which is basically playing with certainty and uncertainty, and then tweaking it in a way that you put certainty to your advantage, so that when you measure the result, you get the result that you want with higher probability. Still feels a bit doesn't feel enough. I have the impression there's more to it, but so far we haven't got many tools to help us do that. The edge gate is the only one that has moved the certainty around at all. To really get things moving, we need a new kind of gate. The gates are acting more than 1 qubit. So one of the most important controlled operations is the control Z, also known as the CZ. This is the one we introduced in level 3. Unfortunately, this is not yet available on the IBM Q Experience as a native gate, but if it were, it would look like this. Really? I thought that was the symbol for swap. So there are a few possible ways we can explain the effects of the CZ. Okay, maybe here, I didn't read that before, so when I played with this game, so maybe that helps. Each of the stories seem to be saying something quite different, but somehow they're all equally true. That sounds dangerous. I mean, why people play so much with analogies sometimes it just makes it worse. And the danger with things that are heavily mathematical is that then you try to make some kind of weird analogy, geometrical analogy. I mean, I don't know. Let's see. It's, for example, the block sphere. I like it, but it's just really limited in what it tells you, right? So it really helps you understand the basics of, what an actual quantum state looks like and what can you do with gates and stuff. But it really it really doesn't it doesn't tell you everything about entanglement and all that stuff, which is really what quantum computing is about. So one is to say that the CZ first looks at the bottom circle of the left qubit, depending of whether this circle is white or black. The CZ either does a Z to the right qubit or does nothing to it. Okay, so the control is the bottom circle of the left. So the left is the control and the right is the, okay. So you here have an example, basically. So the example is that on the left qubit you have a 0, so nothing happens to the right qubit, and here you have a 1. Yeah, okay, but that's okay. So how man, what does a Z do, right, at the end of the day? So a Z is it shifts the phase. So in this example, if we ignore the squares in the middle, we have on the I'm taking a look at the right qubit, which is in a superposition, and so it's in a superposition. So this means that it's either in the plus state or the minus state. But I tend to think that because I know that it's a 0, because I can see here that there's a black circle, this means that this was a 0 before, which means it's in a plus state. So what this Z does is it turns the plus state into the minus state, which is basically also like a superposition, 50-50, but if then you apply another Hadamard, you're actually going to 1. So it changes. So it's an interesting way to see that. Okay, so that's actually cool, because I had the block sphere in mind now while I was reasoning about this, but if you think about a Z being that when you have a qubit that's uncertain, what it does is it flips the certainty around. I don't know if that's something you can say. Certainty in that it's probably not something you can always say, because you can have qubits in really messed up states, but if we stick to the pure superpositions, the 50-50% chances, right? So those superpositions are special in the sense that if you apply a Hadamard gate and then measure them, so if you apply a Hadamard gate, then you're going back to the z-axis. I might be going a bit too far, but what it does in this particular case, and that just might be a way to describe that particular example, is that the Z gate flips the certainty behind a state that is uncertain. So what I don't quite get is why now the white circle that's in the four squares in the middle, it's turned black. Why? Why has it turned black? Absolutely no idea. It's frustrating. Maybe need some coffee. It's frustrating. I mean, why? Why? If that is the information, the state information, this means, I don't know, let's see. Another explanation of the CZ gate, maybe they'll explain that later. There's still another chapter. So another explanation of the CZ is exactly the same as this, but with the roles of the two qubits reversed. Well, okay. Yeah. Why? Okay. In these examples, the right qubit acts like a switch and the left might be a Z. Might get a Z. Okay, but why is that another explanation? It's the same. It just, whatever. So though this is the exact same CZ, it can be interpreted in the completely opposite way. Okay, so okay, it's maybe not the same. What they're saying is, so in this case, what they're saying is that, so they stick to the other one being the control, but here the control is a Hadamard. It's a state in a superposition, and the other one is a known state. Yeah, maybe that's why they painted like that, whereas like they seem to be both control, so it's like they affect each other. So you could intuitively say that when you do a control Z, and one of the qubits is in a certain state, as in like that it's a 0 or a 1, it flips the other certainty. Maybe. It's complicated, man. Where was I? Another explanation of this is that exactly the same, reversed. In these examples, the right qubit acts like a switch and the left one, okay. The third way of explaining the CZ is quite different. We can think of it as simply something that moves circles around. Perfect. Specifically, it swaps two pairs of circles, one pair on the left and another pair on the right. Oh, okay. Now you messed it up even more. Though the interpretation is fundamentally different from the other two, it still completely captures the effects of the CZ. Okay, but that would be interesting because, so seeing the control Z in this way would mean that if I am right and I'm saying that the four squares in the middle are sort of encoding state information, whereas the lighted slots are the actual qubits. Like their concrete information, their particular information. So you're basically here switching, right? So you're saying, no, that's, So you're basically shifting information from the qubit to the state. And, right? That is an interesting idea. I'm not so sure if that's correct, but it's an interesting idea nevertheless. So you basically okay. Still, the game is a bit simplistic, right? And still, that's dangerous to make up intuition based on this game, because this definitely is reducing the actual the actual amount of possibilities, because we're just reducing it to 3 types of circles, right? So an uncertain circle, a white circle, and a black circle. But the truth is, they're much more complex. They're much more complex states. So I'm not so sure if those moves would be the same in those cases. This explanation is not without its troublesome parts. Check out what it does to the circle at the very top of the grid. Oh, great. Oh, great. This is just... It's really complex to grasp what's going on here with these 4 squares in the middle. It's like I could play the game, and I'm gonna play the game now a couple levels, but what this really does is just so I'm not, it's not that I have to get the actual rules or whatever, but complicated. It's the first example. In the first example, the circle at the very top was turned from outline to white, and the second it turned from outline to black. What is the logic behind this? It's possible to solve all the puzzles in this game without understanding this effect. Okay, but if you want to, so it's like just play the game. But if you wanna just shut up and play the game. But if you want to become a quantum programmer, you would probably like to know what is going on, definitely. So we're going to give you the opportunity to find out for yourself. Nice. The only reason this effect doesn't seem to make much sense is that the grid is not quite big enough. Perfect. Awesome. The 8 circles don't fully describe a pair of qubits. Oh, so you see, so I was kind of right in terms of thinking that, so directionally right, thinking that those are supposed to describe the state. So the actual system of 2 qubits. To do this, we need to add another possible question. So another measurement. On the this question can be done with the following gates. Perfect. S transpose, Hadamard, and to keep track of what results it will give, we need to add another circle to our description of each qubit. Here, the new circle is in the middle and has been colored in a differently to highlight it, to describe the possible outcomes of the middle circle and all the possible agreements. Okay, so we're talking about agreements and disagreements. To describe the possible outcomes of the middle circle and all the possible agreements and disagreements with each other and the other questions, we need a grid with 15 circles. Okay. With these, you can solve the mystery of the CZ, and you can also check out how the X, Z, and H gates affect these new circles, as well as trying out new gates like S. Just get playing with the new measurements on the IBM Q experience and use your results to understand the bigger grid. Thank you, IBM. That's actually making me feel really curious about that. I think good. So we know. Cool. That's nice. I'm happy that I've read through that. Oh, still another. Okay. Because it basically means that there is a way to represent the state of a qubit that is not graphical and that it actually, or that is graphical or visual in that sense that you can maybe have an intuitive idea or sense of where your information is and how it moves around. And I think that's the perfect tool set for building quantum intuition. And there's a link to a Medium article, which I will. So. Oh yeah, I actually don't have internet right now. But we can take a look later. Okay, perfect. Nice. Next, Beyond Clifford. All the gates we discussed are Clifford gates, each coming to predator, just swapping circles or flipping them. There is much we can do with Clifford gates. They're key to way move information around the quantum computers. They're also excellent at error correction. Full quantum computation, however, needs something more. We need to move beyond circles that are just black, white, or outline. Awesome, that's what I was saying. We need to get ones that are mostly black, pretty much random, but a bit biased towards white. We need to spread out the certainty rather than keeping it on little islands. Then after swishing it around the grid for a bit, we can recombine it in new unexpected ways. That is a beautiful way to describe that, sir, lady. To do these things, we need to the unimaginatively name of non-Clifford gates. Though there are none of these in this game, the Q experience has as a whole a host of non-Clifford gates you can try. Beyond 2 qubits, the puzzles help you build up intuition and knowledge with just 2 qubits. Once you have that, you can begin tackling larger numbers. To fully describe these qubits, we'll again need to keep track of how it would answer the 3 questions, and we need to keep track of how answers to questions on 1 qubit agree or disagree with others. Agree or disagree. So that's a bit confusing when they talk about agreeing and disagreeing. Wait a second. Maybe that is a reference to entanglement in the sense of they are correlated so that they always agree versus correlated in a way that they don't agree. Maybe that's what they mean. Extend this to 4 qubits and you need a hypercube of a cube of 63 of them for 3 qubits and a hypercube of 255 circles for 4 qubits, and that's probably why you can't simulate quantum computers beyond a certain amount of qubits. Number of qubits. After all, we could visualize what's going on in a large quantum computer easily. It would mean that we could easily simulate it. You have it. But there is a need to build them. By guiding information through the massive space of possibilities, we can find routes from input to output that would be impossible on a standard computer. Sometimes this will be a lot faster. Some programs that would take a planet-sized supercomputer to the age of the universe to solve will be doable with much more reasonable sized quantum computers. Nice. IBM Q experience. It's like I feel I don't even need to play the game. You could have just shared the guide. That's awesome. So I have learned that, okay, so there is a way. I have to explore the Q, I have to play with the Q experience a bit more, but there is then a way so this is a good, smart way to represent the state information. And here they say it represents intuitively agreements and disagreements, which I suspect it means the types of entanglement, right? So an agreement would be that if I measure a qubit to be 0, then the other one is always going to be 0, and if I measure it to be 1, then the other one is going to be 1 always, and that's an agreement because they agree. And then the opposite would be a disagreement. But can you do other types of entanglement? I guess so. So, I don't know, maybe I'll let's just play, maybe. See if we can get to, at least unlock the CZ, so. Whoa, that scared me. Okay. So, So see that the CZ gate has been here from a user interface perspective designed as in like we swap those two, we swap those circles. Okay, so now I've got that. That's an easy one. Okay, next. Next, it's maybe a bit too loud. Easy. Next. Easy. And still, it feels a bit. It's a bit. So just play to play is a bit abstract, right? Because what do you learn with that? I mean, what are we learning here? For example, this is the puzzle 3. So we have. I'm gonna try to read it from an intuitive perspective. So we have 2 qubits, the one on the left and the one on the right, the ones that are highlighted, and they are both white, which means they're both in a state 1. And I don't know how to read the 4 squares in the middle, but I would say that because there's a black thing, it means those qubits are entangled in a way that it's a black, so it's 0, so I would assume 0 means they disagree, but again, I don't know what's the convention. So so this is a state, right? It doesn't matter how we got here, but it's a state that I can read as in we have 2 qubits which are in state 1, and they are entangled, so correlated in a way that they disagree. This means that if we measure 1 to be 0, we know the other one is going to be measured to be 1 in that system. I don't know if that's correct. And then what we're trying to do is, I'm liking that. What we're trying to do is, the target is how can we turn them into, how can we make them agree, right? So how can we make them agree regardless of, because I see the target, it turns them blank, so it means it turns them to 0, but no. Sorry, no, they're still disagreeing. You just, whatever, that's, I got too excited. Okay, so that's just the same. Yeah, but let me just retry that. It means once I apply one gate, now we have 0 and 1, and now, so we have, 1 and 0. But then there's a white thing, which means they agree. That's weird. Maybe they are entangled in a way that they, I mean, it doesn't make that would mean they are entangled in. Are they entangled? I don't know. I mean, I like to think, because another way to read that would be that white means they disagree, which is what we obviously see here, right? So one qubit is 0 and the other one is 1. The other way around, 1 and 0. So by applying an X gate to one of the qubits, I'm basically making them agree or disagree again. Maybe, I don't know. Next. Oh, so now we've unlocked the H gate, the Harmar gate. Play. Okay, so now what we have is, so you see, right? So I'm really curious about how to read the actual 4 squares in the middle. Like, does it matter where the color is? Does it matter where the color is? It's like, because here I would read it the same, right? So there is one qubit which is in the 0 state, and another one which is in a superposition, right? Because it's an outline circle. But we know that in reality it's it's a 0, right? Because we know already the measurement after the Hadamard gate, and actually if we do that, we just move that and we're done with the game, but we're done with the puzzle. But here we haven't really changed, it seems, whether they agree or disagree. I just don't... Okay. Here, well, what do we have here is, so you see why in this case the black thing is on the top, the black circle is at the very top and not where it was before. It seems like because the black circles are, it seems it's in the intersection of where the colored circles are. That seems to be this way. But it's still left to see if there's any other configurations later in the game where that is not the case. So, I mean, yeah, that's an easy one to solve, right? You just move this... Yeah, you see, this is exactly... The colored things seem to be... The colored circles seem to be in the intersection. They seem to be in the intersection. And... I mean, the puzzle is simple, as in we're switching that now, and now that also changed, as in like it's off. But if it's off, I don't know if it means again they agree or disagree. Maybe I've missed that somewhere. No, that just okay. Oh, learn more. Where was that? Agreement, disagreement, blah blah blah. It seems to me like, because good, okay, so I think I can maybe deduct it from here, because it seems like always when there's a white circle in the middle, there are two different ones in the measurement. So it might mean that they disagree. That might mean that they disagree. And when it's black here and both whites are black and both black, so it means they agree. But does this still mean they're entangled? I don't know. I don't know if... So I don't know if that means they're entangled. Oh, and that's a weird one. Okay, so here we have... So here in a state where both circles are outlined, so this means there's no certainty at all, but then we have two circles of different colors inside. That's a weird one. That's a weird one. So I don't really understand yet everything, but I think I'm getting somewhere with that, and I like it. So I think I'll play again. I think I'll keep playing later, and see if we can find other things that help us build intuition with that. But I take away one really good thing here, which is that it's not just about qubits, especially when you have more than one qubit, or in this case two, but the information about the state can also be described in that way. So there's a way to describe that's the information of the system, of the set of two qubits. There's more information than just in each qubit, and that's really at the end of the day intuitively what entanglement tells us, that you can't just take apart the system and then know everything by measuring each of them separately. You have to take a look at the whole system. Okay, sounds good. Then looking forward to play again. That has been indeed helpful, but it also means I had to read through all the learn more to really understand a bit more the thought behind the way this game is designed. Yeah, and I'll read the Medium article, and I will also go play with the Q experience.